Yeah, we got to get them. We got to get them rested so that they'll be nice and hyper and active tomorrow. Exactly. Oh, they're sleeping in a pile in the middle of the floor. That's nothing going on. I'll show, but what's the point?
You said you were going to send out an email for this weekend.
Yeah, I didn't send out an email, but I'm going to tell you all right now what the deal is.
Wait, you have a notebook?
Let's see if it's going to want to share today. Nope. All right, well, here's what I'm going to do instead. Can't I turn this sideways? And what's going on here? Oh, I can turn this sideways and make, oh, well, whatever. Stop share. Hey, Liam.
Oh.
You can't see that.
Big L.
I need to pin myself. How do I pin myself?
You gotta click
On
on
your
yourself.
little window.
There we go. There I am. Woo! Look at me. Okay, so here's puppies.
Wow, that is a lot.
There's 7 puppies. Yeah. So, so tomorrow, between the hours of 1 and 2, we will be on our porch with puppies, and we'll welcome any and all visitors who'd like to come by and pet some pups and play with some pups. I'm on Oak Street, 43 to be specific. Oak Street is the one that goes between Highland and 2nd Street and ends right at the park. It's the one that goes east and west between Center and North Street. Both of which go well past 2nd, but Oak Street ends at 2nd Street. We're near the top, so it's straight up the hill from here. We're near the top on the left as you're going up the hill. It's a blue house, but it will be hard to miss because it'll be the one with the puppies out in front.
Will you be mad if we stay the whole time?
No. Feel free to stop by and hang out. We'll have some chairs out. You can just hang out with puppies for a whole hour.
It's in my calendar as puppies with like tentacles.
You're welcome to, Javon.
Oh, well, I'll be working then.
Oh, that's sad.
But I'm sure it'd be great.
Knock on my door any other time, Javon. You can come in and see the puppies.
For another week.
For another week. That's right. They'll be gone after that. But so will all of you, pretty much. So.
Oh. I gotta do that.
Right. So tomorrow, 1 to 2 in my front yard. Come by, play with some puppies. What else was I going to say? I don't remember. Oh, right, ringworm. Full disclosure, that's getting a lot better. They've been medicated for 2 weeks now. All of them look phenomenally better. There are still some spots on puppies. There's still eye patches, and they still kind of look all kinds of weird in places. But I don't think it's that contagious anymore. But full disclosure, puppies have ringworms. We'll have hand sanitizer. We'll have soap and water if you want to wash your hands afterwards. We may even have gloves available if you feel more comfortable with that. But just full disclosure. And even if 6 of us have been in the house, I think I emailed, no, I didn't. 4 of us have been living in the house for the full 7 weeks that the puppies have been alive. They've had ringworm the entire time. One of us has actually contracted ringworm, and it's a little spot on Hannah's leg, and it's occasionally itchy, and she just has to put some lotion on it. It's not even that big a deal if you do get it, but full disclosure, puppies have ringworm. Anyway, those who are just coming in, puppy meet and greet tomorrow from 1 to 2 in my house on Oak Street. Cool. All right, so next up in the agenda is Astrobites by Visma. Take it away, Visma.
Stepping carefully over that. All
All right, so I'm Visma, and part of the reason I chose this astrobite was the delightful title here, Bursting the Hubble Trouble Bubble, Measuring the Hubble Constant with Fast Radio Bursts. I'm also interested in the issues with the Hubble constant, and I first learned about those in a virtual lecture that I went to over break, so that was cool. The Hubble constant refers to the current expansion rate, let me stand in front of the camera, of the universe. Pretty much what's going on with this is that the Hubble constant, as inferred by studying the cosmic microwave background, is incompatible with the value inferred by studying distant supernovae. So those are the two methods that we currently use to determine the values for the Hubble constant, and they don't agree. This is a pretty big problem because the Hubble constant is used to figure out the age and also just the history of the universe. So that's pretty important. We would like to find a way to make them agree or figure out which one is right. The solution is trying to find it through other measurement techniques, which include distance calibration based on the tip of the red giant branch, strongly lensed quasars, something called maser emission, and signals from compact object mergers. These different solutions tend to side with either one or the other observation. So sadly, they have not ended up being very helpful. But there is also, no theoretical explanation of the problem that is convincing. So this paper tells us how fast radio bursts, or FRBs, as I'll be calling them now, might be able to provide us with better evidence. Fast radio bursts are bright and energetic short pulses of radio waves on the timescale of milliseconds. And we don't know a lot about where they come from or how they're created, but some of them repeat either with a fixed period or irregularly. So we're mostly interested in the ones that repeat with a consistent period, because with those, we can look at the redshift of them and measure it, and that can be used to figure out another value for the Hubble constant. They undergo some sort of complicated dispersion just through traveling through how far they travel, and then that will be able to also be analyzed. They also come from outside the Milky Way. So like I said, the redshift can be measured, and then the Hubble constant can be determined from that. There are currently 9 FRB sources that are being used in this article, and there are 118 total verified FRBs, and they're expecting to find lots more of those in coming years. This article was just written this year, so very new and exciting stuff. This graph, it'll give us a different value for not a different value necessarily, but another value for the Hubble constant that doesn't rely on the current methods of finding it. So this is the dispersion measure graph. So on the bottom, we have the redshift that we see, and on the y-axis, we see the dispersion measure. So there are 6 gold sample points that are the best ones that they're using, and the 3 other ones are just not as certain somehow. So this is all 9 of the FRBs that they're currently looking at. The error bars include estimated scatter, and it's pretty interesting to see how that correlates. And this is my favorite graph from the paper. And this is the probability density functions for the various methods of measuring the Hubble constant. So we can see all the different values for the Hubble constant along the x-axis, and then the probability density is on the y-axis. So I'm not completely sure what all of the red and yellow lines mean, but they're combined with the fast radio burst data is combined, and that is the black curve. The gold fit is the dotted line. So that's showing what is closest, and that appears to be closer to the value of the cosmic microwave background instead of the faraway supernovae. So that is pretty interesting. As for the future prospects of this project, it is expected that many more FRBs will soon be found, and they're working on how many events would correspond to like a certain percent of accuracy for a distinct measurement. And this is exciting because it'll allow astronomers to be able to use FRBs to measure the Hubble constant independently from the cosmic microwave background or the faraway supernovae. Do we have any questions? That's all I've got. Yes.
Did they talk at all about whether or not these
Fast radio bursts.
Fast radio bursts. Did they talk about whether or not the numbers they're getting from the fast radio bursts would shed light on why those other two Hubble constants are different, or just that it'll give us a Hubble constant?
Just that it'll give us a Hubble constant. They really didn't talk about like why it would differ from the other ones.
I think the point is it's independent. Right?
Yes,
All of these are
yeah.
independent measurements of the same quantity, completely different objects. And any systematics that are present in one of them, you hope isn't present in another one. And if all of them agree and one of them's off, then you have more faith in that one. But right now we have two really good ones and they don't agree with each other. So getting more very small error bar values of the measurement Hubble constant is very important to figure out which of those two is right and which is probably suffering from some sort of systematic offset.
Yes.
So you said that the fast radio bursts, like people don't know where they're coming from.
Yeah, there were
other theories.
They didn't go into depth in that very much, but there were like a couple ideas. I did not include that in my presentation, but yeah, it's interesting because some of them like just happen once, some of them don't really have a pattern, and other ones repeat. So
Weird.
yeah, something far away is doing that.
When you said like the repeating ones, my first thought was like a spinning neutron star, you know?
Ah,
Like, what are those things?
Pulsars.
Yeah, pulsars, yeah.
Yeah, but these are, I think, I don't know for sure, I'm guessing much longer periods than pulsars. Like pulsars are
They're spinning.
milliseconds per second.
It's mentioned in the article magnetars, isn't it?
Is it?
Yeah. So I think they were saying that it might come from magnetars.
Oh,
Ah.
what?
It's a neutron star with a really powerful magnetic field.
Oh,
It's
okay.
the magnetic equivalent of a pulse.
yeah, these are on the scale of milliseconds.
Oh, are they?
Yes.
Oh, okay. Interesting. Fast, I guess they call them fast, don't they?
Yeah. Anybody else? Okie dokie. Thank you.
I think okie dokie.
Yeah, very professional of me.
It's just all these
I love the
numbers.
little, like the sad face. Like, none of these are really effective. I'm like, oh my God, that's so sweet.
Yeah, so this is showing the present problem, right? This is the supernova stuff. This is the cosmic microwave background, and these are, I think this is the 1 sigma and 2 sigma error bars on these numbers, and not even the 2 sigma error bars overlap. It's gotten worse over time. Like usually you get multiple measurements and they start converging over time. These two have been diverging from one another in terms of the error bars for quite some time, and it's gotten to be a problem. I think each of these curves are the individual FRBs, yeah. And this is the average one. So obviously this isn't very effective yet, right? Both of these are perfectly compatible really with the measurement that was made. But if they can get, 10 times that many, now maybe you're talking about actually narrowing in on one of those two. The other cool thing about this, I thought, was actually how they're measuring the distances. Did you catch that? It's this dispersion measure. So I guess as radio waves pass through the intergalactic medium, the universe, they get slowed down by stuff in the intergalactic medium. And so but how much they get slowed down is I guess it's like an index of refraction. The universe has a very, very small but non-negligible index of refraction difference from 1. And so different wavelengths get slowed by different amounts. And so by seeing when the, short wavelength radio waves come in faster than the long wavelength radio waves come in, and measuring the difference in timing between the two, they can actually determine how far away these things are because they know how much space it's passed through. It's very clever.
And age of the Earth is not over H0, right?
Well, yeah, so the age of the universe.
So just lied to 16 kids the other day.
I mean, yeah, so here is, let's say, some R factor of the universe, some typical distance between galaxies as a function of time, right? If you have, so there's, there is so we're here, right? We have a certain R value, let's say 1, and a certain slope of the Hubble constant. So with no dark energy, like let's just assume that matter is simple, you've got an empty universe, so it should be just expanding at a linear rate. If there's matter in the universe, though, the matter will slow the expansion rate down. So depending on how much matter there is, it can be a little bit of matter, or it can be a lot of matter. And what the future of the universe will do depends on how much matter there is. If there's too much matter, the universe will stop expanding at some point and then crash back down itself. So I lost track of myself. What was the question? Oh,
Age of the universe.
age of the universe, right. So 1 over h0 is just taking the current slope of that and extrapolating it back to 0. But yes, if you do 1 over h0, this is what we tell our intro astronomy students. That is just taking this line straight back. We know that can't be right because there is matter in the universe. And so, we measure the shape of the universe too, and it looks like we're on this line. But if you use this one, you get like 11 or 12, and that's probably not right either because there's globular clusters out there that are 12 or 13, and that's a problem. Anyway, dark energy, none of this takes into account dark energy. We think there's a cosmological constant. There's an extra term in GR, which is permissible mathematically, that is a repulsive force that Einstein actually used to preserve the steady state universe, which he thought the universe was infinite at the time because Hubble law hadn't been discovered yet. And he needed this repulsive force because he realized that this was a problem. There is no such thing as a static universe without this. If you have a universe that's just sitting there not expanding, it's eventually going to collapse back in on itself if it's got matter in it. So he needed this. If you tune it to exactly the right number, you can have a universe that is flat and static and unchanging if the outward pressure exactly balances it. Well, we measure supernovae, and lo and behold, the universe is accelerating. We need this constant anyway to explain the observations, and that curve looks something like this, right? It just so happens that the naive way that you would calculate the age of the universe, straight back to this, agrees pretty much with what you get from this actual universe where we're started off contracting or slowing down, and now we're speeding up on the expansion of the universe.
No, not a tangent line, but like a tangent curve.
Like they're all.
Like
Yeah.
it follows
Oh,
the
I see a tangent curve. Yeah,
Yeah.
I see what you mean. Yep. Yeah, it does come like that. Yep. So there you go.
No, I brought that
But
up.
that was a very long-winded answer to your question, which is probably not at all what you were asking anyway.
No, that was, and then the second half was I was mentioning that I noticed it was a smaller number, which I would be more in favor of. I would say it's more than 14 billion years. So to see that it's like close to 60.
Do you have a reason for your prejudiced opinion?
I don't know. I didn't like the high numbers. I just never liked the.
You like an older universe?
I think so, yeah.
Okay, good to know. We all have our
Hey, that's
preferences.
another data point, right? Joe?
Yeah.
Yeah, so that's very relevant and very cool and very not related to this class, but that's okay.
Yeah, Taylor, what are your error bars on that?
Yeah, what's your preferred Hubble constant? Do you have a number that you prefer?
I mean, I definitely like in the 60 range.
You like in the
I think
60s
I like
better?
the 70 ranges.
Okay, good to know. Just so you know, when I was taking astronomy, like there was a camp that thought it was 50, and there was a camp that thought it was like 100. Like we didn't know what the Hubble constant was of a factor of 2 20 years ago. So the fact that we're doing pretty well, even now, that we're debating between 68 and 72, it's not that bad. Pretty good, astronomically speaking.
I feel like astronomy like gets closer, and then like they should just stop because they get closer and they're like, crap, we figured out 5 more things that are all problems. We're trying to really like decide if this.
Well, right. We all need jobs, though, right? If we run out of questions to ask, then what are we doing here? What's the point?
Just keep asking questions. Keep that job.
Exactly. Okay. Let's look at the astronomy picture of the day today. Hey, look at that. It is a rocket ship in an old-timey photograph blasting off from Cape Canaveral Space Center in Florida. This is carrying a person right there. And that person's name is Alan Shepard. This is 1961. This is the Mercury Redstone 3 launch. This is the launch of the first American to go to space in 1961. This is Alan Shepard. It was a suborbital flight. The Soviet Union had, I guess, several months earlier sent the first human into space. This is the first American ride into space by Alan Shepard. He did not achieve orbit, I guess. He, at least on this flight, less than a month after the first one. 15-minute suborbital flight, 116-mile altitude. So he was in space. But again, in order to achieve orbit, you have to be going at like 8 kilometers per second, and he only achieved 5,000 miles per hour. I don't know how that rocks, but it's less than a suborbital speed anyway. Did Yuri die?
Didn't he?
I don't think so.
The guy that burned up on re-entry?
No, I think he survived.
Who was the guy that was sent up knowing that he was going to die for
I don't know.
re-entry and then did?
No, I think Yuri Gagarin.
There were a few cosmonauts that didn't make it, and the Soviets were okay with that.
Yeah, right.
Like,
There were a few Americans who didn't make it.
Was the Mercury rockets the Nazi guy that we smuggled on?
Oh yeah, yeah, right,
There's a really good show.
So, I
on
mean,
Disney
we weren't-
Plus about the
We weren't.
Yeah.
worried.
right. No, there was Werner von Braun
Yeah.
definitely taught us how to make rockets because it's hard. And the first, I don't know, dozen attempts that they did of launching big rockets failed miserably. There's some spectacular footage of failed rocket launches if you ever want an entertaining half an hour of watching before we figured it out. So
Just billions of dollars.
Was there a astronomy picture today for SM-15 that actually landed?
for,
Starship? You know how like
yeah.
SpaceX, like
Oh,
all
that
of their
one- we had
all of
one
their
that didn't
space
blow up.
starships have been crashing. and stuff?
Yeah, no,
It did-
I didn't notice one.
It didn't crash on Wednesday. It landed successfully.
Marcus
I
was
didn't see
telling me
that.
How excited his son was because the one landed like
This is
his son
hilarious.
likes watching them blow up.
Right, Flynn's all about the
And
explosions.
the one landed and then it was fine, and then like 5 minutes later it blew up, and he was so excited.
He's like-
Yeah, yeah.
That story he told us was Flynn said, "Dad, is it going to explode?" He said, "I don't know." And then like 30 seconds later, it explodes. He's like, "Yeah, woo!"
No, I made my biology teacher watch the live stream right before our lesson.
I'm so disappointed from one.
I guess Alan Shepard did actually go to orbit, not only orbit, but to the moon. He was on the Apollo 17 mission, 14 mission. It was on here. I read it. Oh, Apollo 14. There it is. Oh, that's fun. There you go. And it wasn't Apollo 13, which didn't actually it went to the moon, but it didn't stop. They just came right back because of problems. You can watch that movie too. Okay. It does have Tom Hanks in it. Okay. What are we doing today? It's the penultimate class of the semester. It is. Let's see what I've got here for a keynote. I should have looked at this beforehand.
I feel like there's gotta be something
Still on white dwarfs?
We're still kind of on white dwarfs, yeah. Right, so here we go. This is important. So let's, I got some good stuff here. Good thing I'm prepared. Okay. What's that?
White dwarfs are fun.
White dwarfs are fun. They're very cool. So I think we had, at the last class, gotten to not a fun galaxy.
That's the black hole.
It's supposed to be.
Oh.
But it was Johan. He's not in this class. He doesn't.
It's not strong.
Not that anybody in this class
I
does.
told
know
them
this.
just don't throw anything. You can say the light isn't escaping it and you just can't see it.
I think we had gotten to this result at the very end of class. M times V equals constant for white dwarfs. Yeah?
Yeah.
Okay, cool. So this implies, of course, that the more mass a white dwarf has, the smaller it gets, which is weird. If you do so R is proportional to m to the minus 1/3, something like that. That looks right. That is not this curve. That is this curve, right? This will never actually go to 0, but right. So this is all non-relativistic, right? We have not taken relativity into account. But as you know, as you make the things more and more massive and make the things smaller and smaller, the density has to go up and up and up. And that means that the Fermi energy is going to be going up and up and up. Because the higher the density, the higher the Fermi energy. Remember, the Fermi energy is that energy at which all of the states have to be occupied for a completely degenerate gas, right? And the more you try to squeeze these in, the higher that Fermi energy becomes. And the faster those electrons have to be moving, even at the minimum energy and lowest temperature. So even at 0 temperature, there have to be some of these electrons that are moving as fast as that Fermi energy requires it to be moving, because that's the dictates of quantum mechanics. As that Fermi energy approaches, and as the velocity implied by that Fermi energy approaches the speed of light, we run into a problem. So relativistic effects are going to become important fairly quickly as we add mass to this thing and it gets denser and denser and smaller and more energetic. We're going to be pushing those electrons to higher and higher energy levels. And eventually, they're going to be moving so fast that relativistic effects are going to become important. So this is in the limit of non-relativistic particles. A simple treatment of relativity and by that I mean just set V equal to C and don't worry about all the other weird stuff that happens, gives an upper limit to the mass of a white dwarf. So again, if you take, and again, this is not the simple version. This is the very complicated version, which includes all those relativistic effects. If you don't take it into account, you get this nice blue curve. You don't have to worry about any of this stuff. But we know that relativistic effects are going to become important, and it makes your problem worse. Instead of this propping up your star and making it not collapse further, it only makes the problem worse. As you add more mass, it has to get even smaller, faster. And it has the effect of causing the radius to go to 0 at some point, which this would not imply on its own. And that's a problem, right? And so that sets an upper limit for the mass of a white dwarf. And that upper limit is set by, again, just taking the mass. I think the equation we had before, maybe we didn't have, we had a pressure equation. We had an equation that had the density and the radius. And I think if you plug in V equals C, then you can solve for mass, and that gives you this. This is the upper limit. Again, just simply trading B for C. You get, I'll put squiggle equals because this isn't exactly right. 18 pi to the 2/3 over 10 h bar squared over g times m. Oh, that's not right. Oh, dang it. This is all wrong. I'm looking at the wrong thing. Sorry. 3 square root of 2 pi over 8 h bar c over g to the 3/2 z over a 1 over mh, some of the stuff you look familiar, squared. And these are all constants, except for z over a, which is always going to be about 1/2. Look at all the cool stuff that's in there. This is one of the coolest results that we're going to write down in class, because look at all the stuff that's in there. You've got gravity, there's big G. You got quantum mechanics, there's h bar. You got the speed of light in there. All this good stuff, all this good physics in one, it's not a pretty equation, I wouldn't say, but it's one equation. And it's pretty much all constants. If you plug in 1/2, you can plug numbers into this. What do you get? You get 0.44 solar masses. If you do it right, and you do take all of the relativistic things into account, a full derivation, oops, sorry, screenshot it. Yeah.
So I'm a little bit confused on the relativity. You're saying that at the upper limit of mass for a white dwarf, the electrons will be moving at the speed of light?
Yes. I'm saying that if you try to squeeze this thing any closer together, the electrons are moving up into regions where they have to move faster than the speed of light, and they just can't anymore.
Gotcha.
So the Chandrasekhar, so this was first derived by probably the most, the best theoretical astrophysicist of the 20th century, Chandrasekhar, and he derived what is now called the Chandrasekhar mass limit, which is the full relativistic treatment of all of this stuff done right by geniuses. You get 1.44 solar masses, and the curve that you get from the full relativistic case is given there.
So what's the 0.44 solar mass?
This is just a simple, let's just exchange V for C. It's not right, but it's going to give us a number that's in the right order of magnitude. And it is in the right order of magnitude. It's only off by about a factor of 3.
Well, so I was going to say, I thought that we worked with white dwarfs in the homework that were bigger than that.
Yes.
Yeah.
This is not the true white dwarf. This is the true white dwarf. This is the full treatment. Full special relativistic treatment. Full treatment of relativism. Okay. And you can see this. The ultra relativistic limit. You cannot make a white dwarf that has a mass greater than 1.44 solar masses. Great.
What happens if you try?
Well, good question. Because certainly you can have a white dwarf in space and you can dump matter onto it and it can exceed the Chandrasekhar mass limit. We think a type 1a supernova is the result of that. And what does it then collapse into? It can no longer support itself. It's no electron degeneracy is no longer a thing. Things have to happen. What happens then? That's the topic of the last topic of the whole semester, which is neutron stars. So some quick history. Anybody know what year the neutron was discovered? I was shocked. I'm always surprised at how late it is in the
1900s?
Good guess. It's way later than that.
Yeah, because the electron was,
It's not that late.
the electron was like the 30s.
Was it?
think so. It was by the guy that Wilberforce did his PhD with. I can't remember the actual guy's name now, though.
1932 is neutron discovery, which is quantum mechanics is known by this time. The Hubble law is known by this time. Like, we didn't even know the neutron was a thing until 1932. It's kind of wild, isn't it? I thought we had understood atoms well before then.
So the Bohr model would have had to have come after that?
Yeah, well, do you need neutrons for the Bohr model? I don't even know.
What did they think that all of the mass was coming from the proton?
Maybe.
Weird.
I don't know. Anyway, 1934, neutron stars are proposed as a thing. Two years later. That's pretty impressive. We don't even know what neutron is, and then 2 years later we're like, yeah, we can make a whole star out of those. That's probably a thing. And this is Bada and Zwicky. You know, some names you're on into. Famous astronomers from the day. Fritz Zwicky was a particularly colorful guy. He was the one who had all sorts of colorful debates about dark matter in the decades after that. Anyway, he was a pretty major player in the astrophysics community back in the day. So the point of this is, once you exceed this Chandrasekhar mass limit for a white dwarf, what happens? When the mass of a white dwarf exceeds Chandrasekhar mass limit, I say collapse here, but is that really the case? I mean, you've already approaching the Chandrasekhar mass limit, so it's already kind of like a collapse. How? Where do the electrons go? Something has to break down here. What happens to all those things? And this is the reaction that happens. Proton plus electron goes to neutron plus an electron. This is an endothermic process, so it actually takes energy to make this. I think the energies of these are more than the energies of these. So you need a really high kinetic energy electron smashing into your proton to be able to do this. This is actually an energy sink for this object, but it has to happen because it's so hot at this point that that kinetic energy is there, and you can actually have that happen. So that's what we think happens. All of these protons and electrons, or at least 99% of them, or 99.99% of them, or something, have to go away to relieve the electron degeneracy pressure, and then you have a thing that's 99.999% neutrons. And that has its own set of things, because neutrons are also fermions. And you can do all of the same equations that we did for electron degeneracy pressure for neutron degeneracy pressure, except that the pressures are a lot higher because the mass of a neutron is a heck of a lot more than the mass of that's really all it comes down to. You can squeeze them much closer together, and you can get higher pressures just because the mass of a neutron is so much, 1,000 times more than the mass of an electron or so. Okay. What is the radius of a neutron star? Again, you can go back to, I don't think we actually got this, but in the process of deriving this, well, we can actually get to here, right? This constant is knowable from the things we wrote down in class last time. And the mass of the electron, I think, is in there. You substitute the mass of a neutron and plug that constant in there, you can solve for the mass of a neutron star too. It's basically exactly the same physics. And you get this number, you get this equation. Again, this is non-relativistic, so this is going to be an approximately equal to. And there's some other interesting things that go on with neutron stars too. Hold on a second. but it's going to have some of the, this is the equation that I was starting to write down before. 18 pi to the 2/3 power over 10 h bar squared over g times the mass of the neutron star to the 1/3 times 1 over, I don't know why the mass of hydrogen is in here. Maybe because it's exactly the same as the neutron, to the 8/3 power. You don't need to worry about Z over A anymore. Z is not even a thing anymore. You don't have any protons left. You don't really have any atoms left. This thing is basically a giant atom because it's at nuclear density now. So this is small, right? For a 2 solar mass star, let's actually plug this into Wolfram Alpha. See what it gives us. What's that?
It's like holding it up.
Neutron degeneracy pressure. It is the same thing that was holding up the white dwarf. It is the fact that there's an outward pressure because neutrons can't be pushed closer together without speeding up and going to a higher energy level. That is the pressure that we're talking about.
That means that there's a upper limit of the mass of the neutron star to them, right?
Yes, it does. Very similar, in fact. Oh, look at this. I forgot I had this on here. Oh, this is actually actual masses that have been measured. Let's look at this. Okay. This is actual masses that have been measured of actual white dwarfs. And again, these are hard to measure, but there's Procyon and 40 Eri and things like that. Yeah, so okay, I'm not sure what the point of that is. I want to go back to this though, because this is important for one of the homework questions. So this is the mass times volume equals constant thing. You're asked in the homework to look at 2 different white dwarfs and see which one deviates more from this line. And one of them is like here and one of them is like here. And so hopefully this is a good hint on what the answer to the question of which one is more different and why, because this does not take into account any relativistic effects at all. And those do become important as you go more and more massive.
Wait, I was gonna ask you which one is more weird. I didn't, are people still doing the homework still? Okay.
It's due next Tuesday, so yeah.
Homework, what? I
The
thought it was
homework is,
yesterday.
it's due next Tuesday.
What? Oh dang, okay. Wow. My gosh.
Yep.
I keep posting about it and I keep panicking, like, wait, am I sure that it's next week?
It is next week, along with the cluster project. So it's not like you should be putting it off till next week, but you still have until next week to work on it. Okay, good. All right, what were they doing? Oh yeah, Wolfram Alpha. I should just do straight, well, what do I got? I misspelled alpha. So let's just type this equation in. 18 pi to the 2/3 power over 10 times h bar. Let's do some parentheses here just so we don't mess things up. Times h bar squared over g times, so let's do a 2 solar mass neutron star times 2 solar masses. That's comfortably above this. 2 solar masses to the 1/3 power. I think you're going to do this times 1 over the mass of hydrogen, all to the 8/3 power. Meters per kilogram. No, so we have a problem here. I think, and maybe because I didn't put parentheses around these. Yeah, you're right. Oh, we have we have a number here that's actually in kilometers. So about 4 kilometers, right? You put 2 solar mass neutron star, about 4 kilometers in radius, right? That's 2 solar masses of stuff crammed into the size of something that's got a radius of 4 kilometers. That would, you know, if it were centered were here, it would not switch out to Canisius Lake. It would barely even make it out of town. Well, I guess Geneseo is pretty small. It wouldn't make it much out of town. For a 2 solar mass neutron star, this is about 4 kilometers. Again, this is non-relativistic, so you have to break a little bit. But again, we've got the same situation we had before. Radius is proportional to m to the negative 1/3 power. This is exactly the same thing we had before. And so the mass times volume of a neutron star behaves exactly the same as the mass times radius of a white dwarf, which means that the more mass you pile on there, the smaller it's going to get. So just like there's an upper limit to a white dwarf, there has to be an upper limit to a neutron star. Again, if you do the detailed calculations, relativistic, you get R about 10 kilometers instead of 4 kilometers. But, you know, within an order of magnitude, you're on something the size of a small city. Right, so holy crap, that's a dense thing. What is the density of a neutron star? Let's just think about that. If you've got 2 solar masses, the density is mass divided by volume. 2 solar masses divided by 4/3 pi times 10 kilometers squared. I think that'll work. Cubed, you're right. Thank you. Yeah, so we're at about, about 10 to the 17, 10 to the 18 kilograms per cubic meter. So here's a cubic meter. 10 to the 18 kilograms inside of that. That's like the mass of Mount Everest or something, crammed down into the size of inside a hula hoop, basically, spherical.
Down below is more dense than that supermassive black hole, at least inside of that radius.
I mean, supermassive black hole,
Yeah, that's maybe true. 2 times the average density of inside a Schwarzschild. That's pretty high.
So what would happen to you if you got near one of these things? Obviously, the surface gravity is going to be absolutely bonkers.
Right.
but-
So, well, I mean, it's going to be really hot, so you're going to burn to death before you even do anything. But, right, what is the surface gravity on the surface of this thing? What was that? GM over R, I think. Let's look at the surface. GM over R. GM over R squared. I think that's right. G times 2 solar masses divided by 10 kilometers squared. Yeah, that's right. 10 to the 12 meters per second squared. So, I mean, you're going to be a puddle of neutrons in about before anybody can even know what's going on. Yeah, on the surface. The surface gravity is so high. I mean, these things are, so if you had a perfectly neutron star that's perfect. Let's I got some cool video graphics here too. Hold on. So here is, what am I looking at here? Oh yeah, it doesn't matter. This is, the size of a neutron star over Vancouver, right? This is most things in astronomy you can't really wrap your brain around. And certainly there's lots of things about neutron stars that you can't really wrap your brain around, but the size isn't one of them. You can actually kind of picture how big this thing is over a large city. Well, that's crazy. But the features on here, so the surface gravity is so high on the surface of a neutron star that there are no hills, there are no ridges, there are no canyons, there are no valleys. Everything gets squeezed down into its lowest possible energy state. This is as good a perfect sphere as you'll probably ever get on this size, because there's no other choice for it. The surface gravity is so high. Something like, I can't remember, if the Earth had the similar featureless surface, the biggest up and down things would be like an inch or something on the surface of the Earth over the entire spherical object of it. Right. So this is as dense as normal matter can get. This is nuclear density. Most of the time when we're looking at this stuff, it's almost all empty space because the nucleus is so tiny and the electron cloud is making the space and the volume of the thing. Those electrons are gone now. This is basically a giant nucleus at nuclear density. How many nucleons is that? What is the A of this nucleus? We can do that pretty easily. 2 solar masses divided by the mass of mass of neutron. That's how many neutrons there should be. What? Go away. What? Why would you do that? Anyway, kilograms per kilogram. It's 10 to the 57. This is an A equals 10 to the 57 nucleus, right? And it's probably got some protons in there too, even though most of them have gone away. An if 99.999% of them have gone away, that's still 10 to the 53 protons in your nucleus, right? This is a Z equals 10 to the 50 something atom, right? Which isn't even really a thing because no atomic physics would ever even really be applicable here. Okay, we'll talk about, we've only got a little more to go. We'll talk about the equivalent of the Chandrasekhar mass limit for neutron stars on Monday. Have a good weekend. Don't forget puppies tomorrow between 1 and 2. And have a good weekend. Don't forget Kappa next week. Don't forget cluster assignment. You should be working on that. Yeah, great. See ya.
Oh my gosh. I thought it was due yesterday, so I did it.
Oh, well, now it's done.
Now it's done.
Congrats.